So this is the final section of parametric curves with calculus. So here we're going to do three different things, which is basically area, arc length, and the surface area. So the first thing that we're going to do is try to find the area with parametric equations. So these formulas you've already seen before. You can write them again if you want. Again, they're going to be given to you. So we're first going to start off with area. Okay, so we are given that the area of a parametric equation or parametric curves is just basically taking g of t multiplied by the derivative of f of t dt. Now, the derivation is not that bad. You can go ahead and you can skip through this if you want to, but I'll kind of show you where exactly this is coming from. So basically, we know that area is the integral from a to b of f of x dx. Okay, so let's just say my y is going to be this function f of x. Now, because we can parametrize x, well, we know that x is just a function of t, and we know that y is a function of g. Well, what we can do is we can take this x and write it as f of little f of t. And which we know that this whole thing is just basically g of t, because that's what y is equal to. So what I'm going to do is I'm going to plug this guy, or basically this thing, this information over here. So I'm going to have area is equal to the integral. Now there's going to be f. Now x in this case is equal to f of t, so we're going to plug in f of t in here. Now what is dx though? Because we are now changing the variables to t. Now, what is dx? Well, if I know that x equals f of t, then our dx is going to be f prime of t dt. So our dx is going to be this f prime of t dt. Okay, now notice that everything is now in terms of t. So t is going to be whatever the bounds of t is now. So I'm going to write alpha and beta there. Okay. So now all we got to finish up is, well, what exactly was this equal to? Well, that's just our y, which was equal to g of t. So this is equal to the integral from alpha to beta of g of t, f prime of t, dt. So not a bad proof, very basic. Okay, so now what we really want to do is let's do some problems. Okay, so we'll do a couple of them. There really isn't much to it. You might have to use integration by parts. Sometimes it really just depends on the problem, but remember, use any tool that you've learned in this Calc 2 class. Anything that you've learned, go ahead and apply it. So you can use either partial fractions if you need to. You can use trig sub. We're going to be doing a lot of trig sub later on in the next section, so there's a lot of stuff that you might want to consider. Okay, so determine the area under the parametric curves by the following parametric equations. Okay, so let's say x is equal to 6t minus sine t, and y is equal to 1 minus cosine t, and you want t to be from 0 to 2 pi. Okay, so we kind of said that this guy was looked a lot like a circle. I don't know if this is going to be a circle anymore. I think it's a cycloid. So what you want to do is, the graph doesn't really matter. You know that you want to integrate this from 0 to 2 pi. And you want to do it for the set of parametric equations. So we already have a formula. So we know that the formula is going to be area is equal to the integral from alpha to beta of g of t f prime of t dt. Now remember that f is going to be this guy. This is going to be your f of t. And then your g of t is just going to be your y. So now all we got to do is just basically plug everything in there. So you're going to have the integral from 0 to 2 pi. G of t is going to be the 1 minus cosine t. That's going to be your g. And then your f prime is going to be the derivative of that. So nothing happens to the 6. The derivative of t minus sine t is going to be 1 minus cosine of t dt. So that's going to be the derivative of this. And all we have to do is just take the integral of this. So now we have a 6 and a 6. Let's pull that out to make it 36. Integral from 0 to 2 pi. We're going to have 1 minus cosine of t, 1 minus cosine of t dt. So let's FOIL this thing out. So this is going to be equal to 36 integral from 0 to 2 pi. FOIL this out, I'm going to have 1 minus 2 cosine of t plus cosine squared of t dt. Okay. And now what you want to do is notice that you have this cosine squared of t. One way that we can do this is rewrite it using the half angle formula. So this is going to be 36 integral from 0 to 2 pi, 1 minus 2 cosine of t. This is just equal to 1 half 1 plus cosine of 2t. Okay, we can FOIL that out. That's going to be 36 integral from 0 to 2 pi, 1 minus 2 cosine of t plus 1 half plus 1 half cosine of 2t. I can collect now the 1 half and the 1. Integral from 0 to 2 pi. This gives me 3 halves minus 2 cosine of t plus 1 half cosine of 2t dt. And now we can just take the antiderivative of this. So we have 36. This is going to be 3 halves t. This is going to be minus 2 sine t. This is going to be 1/4 sine of 2t. This is going to be from 0 to 2 pi. Okay. Now notice that when I plug in the 2 pi and when I plug in the 0, you can just put this in the calculator. The sign is going to be 0. So the only thing that's really going to matter is this guy, this 3 halves t. So you're basically only looking at 3 halves. This 36 times 3 halves times 2 pi. Because if you see, when I plug in the 2 pi in here, well, that's just going to be 0. When I plug in the 0 in here, this thing is also going to be 0. If I plug in the 0 here, you're also going to get 0. So all that really matters is just this, this guy. I'm left with is 108 pi. So this is my area. Okay, so these problems are really nothing really to it. You just want to be able to just use the formula and apply it. I think the difficult part is to be able to do the integration. That I think is the difficult part, but there really is nothing to these formulas. The formulas are just very basic. You just have to be able to do the integral. Okay, all right, so now let's work with arc length. Okay, so with arc length, we basically are doing the same thing. So we know that the arc length in this case is going to be the integral from alpha to beta of the square root of dx over dt squared plus dy over dt squared dt. Okay, so this is basically for the arc length. Okay, so I'll in order to kind of do this, remember that from Calc 1, the arc length of a curve in just regular y equals f of x, okay, where x is between a to b. If you want to find the length of the curve, so basically if you have a curve, kind of looks like that, and you want to figure out how long this curve is, from Calc 1, we said that L is equal to the integral from a to b of the square root of 1 plus dy over dx squared. This is what we learned. Okay, so to derive this formula, I won't derive the whole thing, but basically all you got to do is take this dy over dx, and we know that this is just dy over dt, dx over dt. So what you want to do is plug that guy in there. Okay, find the common denominator between these two, change your dx, okay, into a dt, and you will see that you get this particular answer. Okay, I don't know why I changed color. I don't know where. um, but that's basically all it is. Okay, so what we'll do in the next video is we'll do a problem with arc length, and then we'll do one for surface area.